And in our previous discussion, we have discussed about the equilibrium. We have discussed about how to express the torque and the potential energy of an extended object using the position of the center of mass. I share the screen with you now. Do you remember this? Okay. Now we can actually find the torque, okay, due to the weight of an extended object by imagining all the mass of the object to be positioned exactly at the position of the center of mass. So the torque will simply be given by mgx, where mg is of course the mass of the weight of the object, and x is the distance of the center of mass from the line of from the perpendicular distance of the center of mass from the point of suspension. Okay, so this is the idea. And you can also express the potential energy of an extended object by using the height of its center of mass, Z. So the potential energy of the extended object, mg, Z. Okay, and we also have discussed about a hanging object, an object that is pinned about a point, feet rotate about this axis O, and we say that the object will be at a stable equilibrium if its center of mass is directly below the point of suspension. Okay, so in this configuration, on the figures in the figure on the right, the center of mass position is exactly below the point of suspension, and that is the most stable equilibrium position. If you tilt the object slightly, the center of mass position will be raised, and so its potential energy will be raised. So remember, when we talk about equilibrium in chapter 5, we emphasize that the stable equilibrium is the position where the potential energy is at the minimum. So if you displace the object from this position and you find that the potential energy is raised, that means this position has the minimum potential energy. So you can consider this position as stable equilibrium from an energy point of view. Okay, and you can also find that from the point of view of torque, if the object is slightly displaced, the torque produced by the weight of the object will always tends to decrease this angle theta. So it will restore the object to its equilibrium position. Okay, so from both the point of view of energy and torque, you can find that this position is in fact a stable equilibrium position. Okay. Now we discuss about the condition for equilibrium. In your high school physics, you already have meet the conditions for translational equilibrium, and that is you have when your object is not in motion, then the total momentum of the object is 0, and that means the rate of change of momentum of the object is also 0. But the rate of change of momentum of that object is equal to the net force acting on the object by Newton's second law, and so that means the net force acting on the object is 0. Okay, so that is the condition for translational motion equilibrium. Whenever you see an object is not moving translationally, now what I mean by moving translationally is the position of the center of mass. If you find that that object have the position of center of mass fixed at rest, then the object is not moving translationally. Okay, so now the momentum being equal to 0, now I refer to the momentum of the center of mass. Okay, and the net force acting on the object being 0, now I refer to the net force acting on the object, which is equal to the rate of change of the momentum of the center of mass. Okay, now that is the condition for translational motion equilibrium. And I also have another condition now for the rotational equilibrium. Now, even if an object is not in translational motion, it can rotate, right? So in order for the object to be totally in equilibrium, I would like to impose another condition for rotational equilibrium, and that is the object has no rotation. Okay, so the angular momentum of the object about the center of mass is 0. And that means the torque, the total torque, external torque acting on the object, which is equal to the rate of change of angular momentum, is also 0. So you have two conditions now. The first condition is for translational equilibrium, is a sum of all external forces acting on the body is 0. Okay, so it's not acted by a net external force. Okay, there may be internal force, no problem, but the total external force acting on the object, the vector sum of the external forces, will be sum up to 0. And for rotational equilibrium, you will have the sum of all external torques acting on the object measured about any point is 0. Okay. Now, you notice that I'm very careful here because I say the external torque measure about any point. That means you take moment about any point, the total torque is 0. Now, this condition, this careful condition is in fact unnecessary if translational equilibrium is has been met. Now, there is a theorem in mechanics saying that if the body is in translational equilibrium, which means there's 0 net force acting on the body, then the moment of the forces about any one point being equal to 0 will imply the moment of force about any other point will also be 0. There is such a theorem in mechanics, in statics. Now, I will not go into the details of such this theorem, but I just want to let you know that it is sufficient for you if you find that the body is not moving, it is in translational equilibrium, then you can simply take moment. You can simply calculate all the torques about any points on the body. And if you find that the sum of the torque is 0, that means the body is in is rotational equilibrium. You do not need to check all points for taking a moment. You only need one point. If you find that that point, you take moment about that point, the sum of the torque is 0, then that body is in rotational equilibrium. Okay, because there's a theorem in mechanics, in statics, which guarantees that. Okay, but I will not go into the detail here. Okay. So let's have a simple example. I think the example you already have met in your high school study, but I just want to re-emphasize the equation that we used are based on the previous two laws that I have stated. Okay, suppose there is a uniform rod or ladder that leans against a wall. Okay, this is a vertical wall, and the ladder or the rod makes an angle theta with the vertical direction. So this angle is theta, okay? And the length of the rod is L and the mass is M, okay? Now I assume that the vertical wall is smooth so that there's no friction here, okay? But the ground is rough, okay? So on the ground, you have friction. The frictional forces preventing the sliding to happen. Okay, so it prevents the sliding to happen. If you have no friction, then the ladder will simply slide down. So with friction, there's a force pulling the ladder inwards, and that prevents the sliding to occur. Okay, and of course on the wall and also on the ground, there are normal force, and on the wall, because there's no friction, we only have a normal force in the horizontal direction, which I call R. And on the ground, the frictional force is already accounted for. This is F. And so I have another normal force, and that is N, which is normal to the ground. Okay. So here is the force diagram. Now I'm going to use this force diagram to solve the problem. Okay. Now first I consider the balancing of horizontal force. Okay. Now because force is a vector, okay, and this is a two-dimensional problem. So that means what? That means you actually have two equations for the balancing of force. One for x direction, which is horizontal direction, the other for the vertical direction. Okay, and for the horizontal direction, you only see two forces: the normal reaction from the wall and the friction from the ground. And of course, in this diagram, they clearly are equal in order for equilibrium to be achieved. Okay, so R is equal to F. And what are the vertical force? In this diagram, very clearly, you can see that the normal force N from the ground must be balanced by the weight of the object. Okay, the two forces must balance each other. There are no other vertical forces. So N is equal to mg. Okay. Now here we already have finished considering the force, right? And how about the moment? How about the torque? Okay. We can take moment about any point we like. Okay. And for convenience, I would like to take moment about the point P, which is in contact with the ground. Why do I like to do this? Because the problem, the point P has two unknown force, N and F. And if I take moment about this point, I can eliminate them in the equation, right? Because the force act exactly at this point, the two force N and F act exactly at this point, and that means the moment about this point is zero, or the torque about this point is zero. So I don't have to these two forces do not enter the equation. Okay, so that's why I take moment about point P. Okay. Now I have the torque from the normal force R. This is the force R about the point P. And the perpendicular distance is this height, which is L cosine theta. So I have RL cosine theta as the clockwise moment due to the normal force R. Okay, this is a clockwise moment because it tends to turn the rod in the clockwise direction, along the clockwise direction. Okay. And what is the counterclockwise moment? It is by the weight of the object. The weight of the object is mg, and it's the distance, this distance from the point P, the perpendicular distance. And this distance is L over 2. This angle is theta also. So this distance is L over 2 sine theta. So I have a torque as mg L over 2 sine theta. This is the counterclockwise moment. Okay. And the clockwise moment balancing the counterclockwise moment, we have this equation. And so I can easily find that R, from this equation, I can easily find that R is equal to half mg sine tangent theta. Okay. Simply follow from this equation. And since from the first equation, I have R equal to F, so that the frictional force F is also equal to half mg cotangent theta. Okay. Now our problem say I want to find the maximum angle of theta such that no slipping occurs. Okay. I assume a coefficient of friction mu between the ground and the ladder. Okay, so I want to find the maximum value of the angle theta such that slipping will not occur. Now for there is a maximum value of the friction that can be produced from the ground. Okay, and that value corresponding to the coefficient of static friction multiplied by the normal reaction. Now this is the limiting case. The friction must be smaller than this maximum value in order for stability to happen. Otherwise, the slipping will occur. So the maximum value of the friction is mu n, but n is equal to mg, so I have mu mg. Okay. I know that this is the maximum friction, so the maximum friction must be, which is mu mg, must be larger than the actual friction f, which is equal to half mg tangent theta. And then this inequality can be solved for theta. And that means theta must be smaller than arctangent of 2 mu. Okay. Now you can move the 2 to the other side, and you take arctangent on both sides. You obtain this equation. Okay. So that means the angle cannot be too large. It must be smaller than arctangent of 2 times the coefficient of the static friction. Okay. So we have solved this problem. Now, I think most of the calculation you have learned before in high school. The only thing that may be new to you is the use of this coefficient of friction. Okay, the coefficient of friction give you the maximum value of the friction that can be produced in this problem. Okay, so I have the maximum value of friction equal to mu n or mu mg. Okay. Now there are in fact three kinds of equilibrium that is associated with the rotational equilibrium. Okay. Now a simple way to illustrate that is to use a cone. Now if you put the cone with a circular base on the table, on a horizontal table, that is a stable equilibrium. Now why? Considering when you displace the cone slightly about one side, okay? If you displace it slightly, the center of mass position is raised, right? And you can see that the potential energy increase, okay? So this position, when the cone is at rest, this position is the position with the minimum potential energy. So that's why it's stable, right? And you can see from the top, from point of view of the top, if you displace this cone slightly, you can see that the center of mass here will produce a torque that tends to restore the equilibrium, tends to decrease the angle such that the cone will move back to its initial position. Okay, as long as the center of mass position is within this area. Okay, if it displaces too much, the center of mass goes beyond the point of support, then the cone will topple over. But if you displace slightly, such that this center of mass lies within this circular area, the torque produced by it will restore the equilibrium. So that's why it is stable equilibrium. Okay. Now, an unstable equilibrium will occur if you invert the cone and put the vertex and you try to support the cone with its vertex at the top of the table or placed up on the table. Okay, that is unstable equilibrium. Why? Because when the cone is displaced slightly, okay, the center of mass position will be lower. Okay, and so that means there's a decrease in potential energy. And that means the cone at its initial position has the highest potential energy. And the point where there's a highest potential energy is unstable equilibrium. Okay. You remember you learned in your equilibrium, in your work and energy chapter, that's when you have a highest, you have a point with the highest potential energy, that position corresponds to unstable equilibrium. If you displace slightly, the potential energy decrease, that is unstable equilibrium. Okay. And you can also look at it from the point of view of the torque. When you displace slightly, the tip of the cone is so small, it cannot prevent the cone from topple over. You can see that the center of mass will produce at the center of mass there's a torque that tends to topple over the cone, right? The base is so small, it cannot support it stably. Okay, so the torque produced by the center of mass, produced by the weight of the object at the center of mass, will topple the whole cone. And so that is unstable equilibrium. Now there's also a third kind of equilibrium called neutral equilibrium. And for this example of a cone, that happens when the curved surface of the cone is at rest on the table. Now if you roll the cone above that curved surface, you can see that the center of mass position will neither be raised or lower. And that means that is a stable equilibrium. But I will call it as neutral equilibrium because the potential energy is not raised or lower. And there's no torque, actually no torque, that tends to restore or disrupt the equilibrium. And that's why it's called neutral. Okay. Now, if you want to have a more thorough understanding of the idea of center of mass, especially for continuous distribution, and if you want to have a more detailed study of the moment about the center of mass and the motion of center of mass, you are referred to this module by Professor Kenneth Yang. Okay, I recommend you, if you learn more, you always can go to this e-learning module to learn more. Okay. Now then we come to a very important theorem in this course, and that is a conservation of angular momentum. Okay. Now let's restate what is the conservation of angular momentum. When the net external torque, tau, acting on the system is 0, because the torque is equal to the area dt, the rate of change of angular momentum, right? So if the total external torque is 0, that means the rate of change of angular momentum is 0. And that means the angular momentum remains a constant. But for a body that is rotating about a fixed axis, the angular momentum can be written as the moment of inertia multiplied by the angular velocity. Okay, so that is the law of conservation of angular momentum. The total angular momentum of a system is conserved when the net external torque acting on it is 0. Okay. Now I emphasize that although I haven't proved it, but the idea of conservation of angular momentum is still valid, even if a body has a changing angular moment of inertia. A body with a changing moment of inertia means that the body is not a rigid body. It can deform. Okay, when it rotates, the body can change its shape. And so this moment of inertia will change. Now we haven't proved this very general form of Newton's second law of rotation. We haven't proved it. But believe me, even if the I is changing, we still can have this conservation of angular momentum holds. Okay, so that is an assertion. I will come back to this point at the end of this chapter. Okay, but at this moment, you believe me for the moment. So consider a body with moment of inertia change from I to I prime. So if the total angular momentum is conserved, the angular velocity will also change, right? Because the combination I omega is a constant, right? And that means if you change the moment of inertia, the angular velocity will also change. And they change in the opposite way. If you increase the moment of inertia, the angular velocity will decrease. If you decrease the moment of inertia, the angular velocity will increase, such that the product of the moment of inertia and the angular speed remains a constant, and that is the angular momentum. Okay. Now, so if you have a body with I change to I prime and omega change to I omega prime, you have this quantity conserved. I prime omega prime being equal to I omega. Okay. And so you can find a new angular velocity in terms of the old angular velocity and the ratio of the old to new moment of inertia. Okay, so you have omega prime equal to I over I prime omega. Okay. Now let's have some example for you. This is a daily life example. You see a skater, when she contracts her body, she will be spinning faster and faster. Now this is commonly seen in many skating competition, and you can see the skater skating beautifully, rotating beautifully, and when she contracts her arms or contract her legs, she will be getting faster and faster. And that is a very interesting thing to see. I will let you see the video in a moment. Now let's see why this is so. Now you can see if I take a point mass, say I call this point mass Mi, at a distance Ri from its axis of rotation. Now this is from her arm. Okay, so I consider some mass from her arm. And initially, it's at the distance Ri from the axis of rotation, which is at the center of her body. Okay. Now she contracts her arm. So the Ri decrease, it decreases to Ri prime. So Ri decreases to Ri prime. And because the moment of inertia is a summation of Mi Ri prime. So that means when a summation Mi Ri prime square. So that means when Ri square decrease, the moment of inertia will decrease. So I will decrease to I prime. And according to the conservation of angular momentum, because I omega is a constant, so the angular velocity will increase. It increased from omega to omega prime. Okay, so that is a simple application of the law of conservation of angular momentum. Now, I don't know if you have heard about the neutron star. The neutron star is a very compact star that is formed by the contraction of a star that has a mass which may be larger than the sun. A neutron star may carry about 1 or 2 solar mass, or even more. Okay, but it's at the end of a star's life, the star contracts under gravity very violently, such that all the mass is contracted into a small sphere that is as small as Hong Kong. It may be about 20 kilometers in diameter, which is very small. Okay, and in that 20 kilometer diameter sphere, it carries the mass of the whole sun, or even larger. Okay, so that is a neutron star. So you see, it contracts a lot. Okay, the sun is about 100 times larger than in diameter than the Earth, right? And Hong Kong is so small. There's such a small place on Earth, right? So you see, when the sun contracts from say 100 times the Earth radius to a size that is much more than the Earth size, about the size of Hong Kong, that means a lot of contraction. And so the radius will decrease a lot, right? So normally, when a star is spinning normally with a slow rate, when it contracts so much, it will be spinning very fast due to conservation of angular momentum. Okay. And typically, a neutron star, which is a highly contracted star, will spin very rapidly at the rate of several revolutions to 1,000 of revolutions per second. Okay, and because of this such a high contraction, it concentrates the magnetic field. So in the neutron star, you have a super strong magnetic field, and the electron, because they spiral around this strong magnetic field, they will emit the so-called single-joint radiation. And so on Earth, you receive beams of energetic radiation, radio radiation from this neutron star. And so when this neutron star spin, the jets of radiation will sweep past the Earth, and you will detect a periodic signal. Okay. And that is another example of the conservation of angular momentum. Now, this is a demonstration we normally play in a school classroom. Okay, you stand on the rotating table, rotating platform, and originally you have 2 masses on your hand. You extend your hand, so you have a large moment of inertia. Initially, you are spinning slowly. Okay, so you have a large I and a small omega. But when you contract your arms, okay, you contract your arms, the moment of inertia becomes less. So I decrease. And correspondingly, if L remains a constant, that means omega will increase. So you'll be spinning fast. So you will be seeing the person when they contract her arms, he will be spinning faster and faster. Okay. Now I have this video for you. Now you see a professional skater. I better share the screen with the video optimized so you can see clearly what happens. Now you see she contract now. Now you see she's spinning faster and faster, right? Very dramatic. Let's see again. Originally, he stretched her arms and legs and rotating slowly. But afterwards, she contracts her body and spinning extremely fast. Okay. Now, I don't know how you have seen Doraemon. How many of you have seen Doraemon? Read Doraemon comics. Okay. Doraemon has a very interesting thing called how do I say this? I don't know how to say it in English. 竹蜻蜓. 竹蜻蜓 is a kind of helicopter device that is put on Doraemon's head, so that when it rotates, it acts like a helicopter's blades. Okay, and it said that with these blades, it can levitate the bodies of Doraemon and Daihong and make them fly. But it's possible. Physically, if it's possible, I want to ask a question. Now, the blade is actually too small. That is, of course, not physical to have such a small blade to support the whole body. But apart from that, there's also another thing that violates the law of physics. It is due to the conservation of angular momentum. Now, imagine if Doraemon is now accelerating upwards. Imagine now the blade is rotating faster and faster. So it accelerates Doraemon upwards into the sky. But according to the conservation of angular momentum, if the blades increase the speed of rotation, that means its angular momentum is increased. But since the Doraemon together with the blades is a system, it's an isolated system, right? So if the blades has its angular momentum increase, Doraemon must have an angular momentum increase, but in opposite direction, in order to cancel that increase in angular momentum. The angular momentum of whole object remain constant, right? So Doraemon will spin in the reverse direction. If the blade is rotating faster and faster in the clockwise direction, Doraemon will spin in the reverse direction, that is anti-clockwise direction, and he will break his neck. Okay, you cannot imagine a person rotating in the anti-clockwise direction without breaking the body. Okay, so physically it is not possible. Okay. Now, how do helicopters solve this problem? That is an interesting question. If you notice a helicopter, you can see a tail rotor at the end. The tail rotor rotates in such a way to produce a torque to cancel the torque that is induced by the angular momentum. Okay, that is included by the conservation of angular momentum of the main rotor. So when the main rotor accelerates, the tail rotor will tend to rotate such that it produces torque to cancel the rotation that is induced by the main rotor. So that's one way to do it. Now, the other way to do it is to use two sets of blades. They're rotating in opposite direction. Okay, so the total angular momentum will always be conserved. Okay, one blade rotates in clockwise, the other blade rotate in anti-clockwise, so the increase in the angular momentum will be canceling each other. And that's another way to solve the problem. Now let's have a simple example of the conservation of angular momentum. Suppose it is a merry-go-round. A merry-go-round, I consider it as a uniform disk with radius r and total mass m, capital M. Now I consider a boy initially standing at the rim of the merry-go-round, rotating it together with it with an angular velocity omega. But now the boy walks towards the center. He walks a distance of half of the merry-go-round's radius towards the center. So finally, the boy is located at the distance r/2 from the center of the merry-go-round. And I want to find the change in angular velocity due to this motion. Okay. Now, for simplicity, I consider merry-go-round as a uniform disk. So its moment of inertia is half mr squared, capital M. Okay, capital M is the mass of the merry-go-round, and r is of course the radius. So the moment inertia is half mr squared. For the boy, I treat him as a point mass. Okay, I neglect the size of his body. So when initially he's at the distance capital R from the center, his moment of inertia is small mr squared. Now the two moment of inertia can be added together because the moment inertia is a summation miri squared. Okay, so that means if you have two bodies, each contributing to part of the moment of inertia, you can always add up the moment of inertia of the two bodies to get the total moment of inertia. That is always possible. Okay, so you have these two added together, resulting in this expression. And how about the final moment of inertia? The moment of inertia of this doesn't change. It still remains the same. The change in moment inertia is due to the buoy. The buoy is now closer to the center. So its new moment inertia is small m, r over 2 squared, where r over 2 is the final distance from the center of the merry-go-round. Okay, so I have m capital R over 2 squared. So the two added together will be the final total angular momentum, total moment of inertia, okay, which is given by this expression. So I simply use the conservation angular momentum, omega prime equal to I of I prime omega. And when I substitute these two value of I and I prime, I got this final expression. Okay, and apparently you can see omega prime is larger than omega, right? Because of the 4 associated with the m here. Okay, and that just makes sense because now the I is smaller than, and that means the whole thing will be rotating faster. Okay. Now let's handle a more difficult example. Suppose you have a uniform rod. Now this is a top view. I suppose now you have a uniform rod placed on a smooth table, a smooth horizontal table, and the rod is pinned about its center on the table, so that the whole rod is free to rotate about this pin. Okay, and the whole thing is rotating horizontally, so you can neglect gravity. There's no gravity effect because the rotation of the rod is on the horizontal table. Okay. And the total rod and the total length of the rod is small l. The total mass is capital M. And now you have a small mass, which is a plasticine. Okay, a plastic bead, you can say. This small mass has a mass of small m and the initial velocity v. The initial velocity is perpendicular to the rod. So that when the mass reaches the end of the rod, it collides with it and stick to the rod, stick to the end of the rod. So the whole thing rotates with a certain angular velocity omega. Okay, so after the plasticine stick to the end of the rod, the whole thing rotate together about the pin at the center. Okay. Now the most difficult part of this problem is how to write down the initial angular momentum. Initially, the rod is not moving, but the plasticine, due to its velocity at the distance from the center of rotation, it still carry angular momentum. But how do we find that? Remember, we have this definition. Sorry, I should go back a little bit. I want to go back to have you remember what we learned in part 1, because it's quite because this is quite a long time ago. So I would have you remember this. How do you define the angular momentum of a single particle, right? That is a problem. Well, it's easy. If you have a single particle PM moving in this direction, then you resolve the momentum in a direction perpendicular to the distance from the point O where you want to take the angular momentum. So I resolve the M with the component of the moment perpendicular to R. I call this component P pearl. Okay. And P pearl multiplied by R will be the angular momentum for a single particle. Okay. Now, angular momentum is like torque. It depends on the origin that you choose. Okay. So if you take the angular momentum about different point, it has different value. So be consistent with your definition. If you take the torque and the angular momentum about a certain position in your problem, keep that to the end of the problem. Okay, so I now have this origin O as my reference position. So I now have P pearl multiplied by R as my angular momentum. And according to this figure, you have the perpendicular component of the momentum as P sine phi, where phi is this angle, but P is mv. So you have mv r sine phi. Okay. Now, a particular case is that when the mass has a velocity that is perpendicular to the radius r. And in that case, the angle phi is equal to 90 degrees. And sine phi is 1. So you simply have mvr as your angular momentum. If you have the velocity perpendicular to the radius, you simply have mvr. Okay. If you have the velocity at making an angle with the radius, which is not 90 degrees, then you have to consider this sine phi. Okay. So remember this. And we go back now. Now, so the velocity is perpendicular to what? It's perpendicular to the radius r, right? So I don't have to consider sine phi. I simply have m v r, where r is now the distance, this distance, which is half of the length of the rod. So I have mv l over 2. Okay, this is a perpendicular distance from of the velocity vector from the center of rotation. So mv alpha 2. That is the initial angular momentum. Now the final total angular momentum is I omega, where I is a composite moment of inertia of the rod and also the persistent. Okay, we consider them as one body now. Okay, the moment of inertia of a rod uniform rod about center, as we have calculated, is 1 over 12 ml squared. Now you can go back to your lecture notes on this. If you have a rod held about one end, the moment of inertia is 1/3 ml squared. If you have a rod held about its center, then its moment of inertia about the center is 1 over 12 ml squared. And I also have this persistent, which is now as a distance alpha 2 from the center. So its moment of inertia is Lm small alpha 2 squared. The two added together give you the total final moment of inertia. Okay, so you take this value, and when you multiply by omega, that is the final total angular momentum, should be equal to the initial total angular momentum. By the conservation of angular momentum, they should be equal. And so you have this equality. And now you can solve for omega, which is this value. Okay. Now, before having the break, I want to ask you one question. I want you to be aware which physical quantity is or are conserved in this problem. The first thing is, do you think mechanical energy is conserved? That is the first question. The second question is, do you think linear momentum is conserved? The third question is, do you think angular momentum is conserved in this example? Now, of course, I know the answer for the third question. The angular momentum is in fact conserved, right? But why? There is an external force from the pin. The rod is not free. the rod is pinned to the table, which is fixed. So there is external force from the table acting on the rod through the pins, right? If there's external force, how would angular momentum conserve? I want you to really think about this question. And how about linear momentum? If there's external force, will linear momentum be conserved? And how about energy? Will energy be conserved? Kinetic energy be conserved? I have a response. I have immediate response from Mr. Lau. Mr. Lau said that external force produce no torque as R equals 0. Your answer is correct. The external forces from the table on the pin, right? Okay, is acted on the rod through the pin. But that external force acts directly at the center. Okay, and the center O is the point about which we take the moment. We take this position. We take the moment of force. It's about the position we calculate the torque. So the torque of that external force about the center is 0. And that's why the external force does not produce any torque. And that's why angular momentum is conserved. Okay, if you take angular momentum about any point, but not about the center, that would be problematic. Okay, so in this problem, you can only take calculate the torque about the center of the rod, where you can eliminate the force due the torque due to the external force. Otherwise, you cannot make the angular momentum conserve. Okay. So how about the linear momentum? Do you know the answer? The linear momentum is not conserved because what? The external force from the table. Whenever there is external force, linear momentum will not conserve. And how about energy? Kinetic energy is not conserved because it's an inelastic collision. The persistent when it collides with rod is stick to the rod. That is an inelastic collision. So kinetic energy is obviously not conserved. So the only one law that you can use apply to this problem is the conservation of angular momentum, but not conservation of linear momentum and not conservation of energy. And in order to apply conservation of angular momentum, you should be very careful. You have to take moment about the center of the rod, because by doing so, you can eliminate the torque due to the table, due to the force on the table on the rod. And this is the only point where you can eliminate that torque and make the total angular momentum conserved. So that is a simple problem, but there's a lot of tricky thing getting on here. So you have to be very clear about the concept of the conserved quantity. Okay, so let's stop here for a. Let's continue. Now this is a simple classwork. Suppose we have a rotating uniform disk. The disk has a mass m and radius capital R. Initially rotating with angular velocity omega naught. And I have a rod of length 2r. So the rod exactly is a diameter. It's equal to has a length equal to the diameter of the disk and a mass small m. I now let the rod fall gently onto the disk such that the length of the rod spans the diameter of the disk. Okay, so eventually the rod and the disk, due to the frictional force between them, they rotate together. So I want to ask, what is the final angular velocity of the system? The rod together with the rod. Okay, the disk together with the rod. Okay. How would you apply the conservation of angular momentum? What is the initial angular momentum? Initially, the rod is not rotating, right? The rod is at rest. So the initial angular momentum is due to the disk. And what is the angular momentum of this? Can somebody answer me? What is the initial angular momentum of the disk? What's this? What is the moment of inertia of the disk? It is half what? Half mr squared. This is the moment of inertia of the disk. And its initial angular velocity is omega naught. So I omega is half mr squared multiplied by omega naught. The rod is not rotating initially, so it doesn't have any angular momentum initially. Finally, I have what? I have the rod and the disc rotating as a whole, right? They they move together, right? The moment of inertia of the rod of the disc doesn't change. It's still half mr squared, right? But now I have the rod, and the rod has a moment of inertia about its center is 1/12 mr squared. But be careful. Now the radius of the rod, the length of the rod is not simply r, but 2r. So I have 1/12 of m of the length of the rod, which is 2r squared. So instead of just 1r squared, I need 2r squared here because 2r is the length of the rod. Okay. So the sum of these two will be the total moment of inertia, the final total moment inertia, and I multiply by the final angular velocity to get the angular momentum, the final total angular momentum. And by conservation of angular momentum, I know these two quantities are equal. Okay. Now how do I handle this? I cancel half mr squared on both sides. Effectively, I take out a factor of half mr squared, and I'm left with 2 of this. The r squared will gone, I know. And then I have small m multiplied by 4. The r squared will have gone. Okay. I divide the whole thing by half mr squared. Okay. Is that right? So now I have omega be equal to 1 plus what? This is 8. Okay, so this is my answer. Okay. Okay, any problem for this? Now here I have a very interesting example. I put an extension, meaning that I will not test you in the final exam. Do you notice that the cast, when it's dropped from a great heights, for example, it accidentally falls down from the window, it will rotate its body. It will try to land safely at least. Now don't try it with your cat. It's very dangerous. Okay, but the cat has this instinct. The cat will try to rotate its body such that it will try to land safely. It will try to mix its body with its 4 legs facing the ground before landing. Okay, that is the instinct of cat. It can rotate its body in the sky. Okay, so how does the cat manage to do that? It has a trick, and the trick relies on the moment of inertia, and it also relies on the conservation of angular momentum. Now the cat does not rotate the whole body at once, but it will at first it will retract his front body. So imagine I'm the cat. I'm retracting my front body. So I retract my front leg so that the front part of my body has lower moment of inertia. So when I rotate in say the positive direction, in a certain direction, by conservation of angular momentum, my rear body, my leg will rotate in the opposite direction. But I would deliberately want to decrease that rotation by extending my rear body. So I try to retract my forearm and I extend my leg. So my front part of my body will be rotating more, and the rear part of my body will be rotating less in the opposite direction. So that's the trick of the cat. And after I rotate the front part of my body, I now extend my front arm to make the rotation less, and then I retract my legs to rotate my rear part. Okay, and in doing this process, I will be able to rotate my whole body. Okay, now let's see a slow motion. Now the cat will first retract. It's like don't try to do it with your own cat, right? It's very dangerous. Okay, and I better share the screen with you with the video optimized. Can you see? Now, when he rotated the first part of the body, he retract the front leg and extend the rear leg. But the rear leg rotate actually in the opposite direction to his front body. And after his front leg is in the correct direction, he extended, okay, to stop the rotation. And then he rotated, and then he retract his rear leg and rotate the rest of his body. And then eventually he lands with the forelegs facing the ground for safe landing. Okay, let's see it once more. Angular momentum is conserved, right? Let's see once more. Okay. So this is the second part of his rotation. Okay, just to complete the description. Now we have to understand that when we discuss about angular momentum, we have to understand the important fact that angular momentum is in fact a vector. Okay. But how do we define angular momentum as a vector? How do we define its direction? Well, we define it with a right-hand rule. Now, when we say about rotation, we refer to our right hand. Suppose a mass is rotating in a circular motion around an axis. Okay, this axis is the axis of rotation, and the mass is now moving with a linear speed, rotating in a circle around this axis. And how do we define the direction of angular velocity? We define the direction of angular velocity by using the right-hand rule. Okay, now remember when we talk about the right-hand rule, we say the right-hand rule is the only rule that is used in physics. Okay, in physics, in senior level physics, we don't use the left hand or the Fleming left-hand rule or the right-hand rule. We only use the right hand. And because the right hand defines the cross product. And similarly, now we use the right hand to define the direction of rotation. We are no longer using the term clockwise or anti-clockwise because it does not apply to 3 dimensions. If you have a body rotating in 2 dimensions, you can say, oh, it rotates in the clockwise direction, anti-clockwise direction. But when it comes to a 3D rotation, we can rotate about this axis, you can rotate about that axis, and the axis is pointing in 3 dimensions. You cannot simply use clockwise or anti-clockwise. Anti-clockwise or clockwise has no meaning. So you now have to define the rotation or the angular velocity or the angular momentum as a vector. Okay, and you are using the right hand to do that. Now, say if you if you raise your right hand and your forefinger is rotating, is curving along the directions of motion of the particle, then the direction of a thumb will define the direction of the angular velocity and the direction of angular momentum. So if you have a body rotating like this, you curl your forefinger in this direction, your thumb will be pointing upwards, and that is the direction of omega and L. So I write now the omega and L with a vector sign, meaning that they have a direction. Now you can notice that that direction of omega and L, it does not specify the direction of the motion. It only specifies the axis of rotation. So the thumb is actually pointing in the direction of the axis of rotation, where the body is actually rotating about this plane. Okay. Now, if you have a body moving in the opposite direction, you do the opposite. You curl your forefinger in this manner so that it is rotating with the body, and your thumb will be pointing downwards. Okay, so this is the direction of omega and L. Now, although I haven't go into the detailed mathematics, I will amend it at the end of our discussion. But many phenomena about angular momentum have to be understood actually in terms of the vector nature of L and omega. You cannot simply understand this phenomena without treating the angular momentum as a vector. Now, we will leave the more rigorous treatment at the end of this chapter as the extension part, but let us believe that the angular momentum is a vector. And let's see how the angular momentum is conserved if I apply it with the treatment of a vector. Now, here is an interesting demonstration. Now, the demonstration looks like this. A person is now sitting or standing on a rotating platform. Okay, and he's holding a bicycle wheel. And initially, the bicycle wheel is rotate such that the axis of the wheel is horizontal. Initially, the person holds the bicycle wheel such that the plane of the bicycle wheel is vertical, but the axis of rotation of the bicycle wheel is horizontal. And he set the bicycle wheel into rotation. And after he set the bicycle wheel into rotation, he rotates the axis such that the axis of the bicycle wheel is now pointing upwards. And as soon as he do that, he will find that his body will rotate in opposite direction. Okay, and if we invert the bicycle wheel, if we turn upside down, if we turn the axis now to the downward direction, his body will automatically change the direction of rotation. And in short, his body will rotate in a direction which is always opposite to the direction of rotation of the bicycle wheel. So that is very, very interesting, right? Now, I'd let you see the video first before we discuss about this phenomena. Okay, this is the mathematics, but I want you to see the phenomena first. I have a video, although I don't have I cannot show you the real thing. Now, I actually have this set up. If it's not a pandemic, if I can see you face to face, I can show it to you by using my own body. But now I'm not able to do so, so I have to rely on video. And the video is like this.
Try not spinning. My assistant's going to come and spin this for me.
Now the axis of the bicycle is in horizontal direction, and he spin the bicycle wheel. No? Now let's see what will happen when it turns the bicycle wheel with the axis in the vertical direction.
Some angular momentum. Now when I rotate it.
Now you see his body rotate in the opposite direction, right? When the bicycle wheel rotates in the clockwise direction, in the anti-clockwise direction, his body rotates in the anti-clockwise direction about the chair.
Start to spin. If I want to stop myself.
Now he reverted.
Stop. If I go the other way.
He go the other way, and his body reverses rotation.
I spin back around.
You can do it again. Okay. Now let's see again.
Rotate it. Start to spin. If I want to stop myself. Stop if I go the other way?
Go the other way. Okay. So that means what? That means his body and the bicycle wheel always been in opposite direction, right? And why is it so? We have to understand that this phenomenon only from the point of view of the vector nature of angular momentum. Okay, we go back to this slide. Now, initially, the person is holding the bicycle wheel with its axis in the horizontal direction. So there's no component of angular momentum in the vertical direction. The only component is in the horizontal direction. But in that direction, angular momentum is not conserved because you have external torque from the ground. But in the vertical direction, because the chair is free to rotate about the vertical axis, so the angular momentum about the vertical direction is conserved because there's no external torque. We assume that there's no friction and the chair is now rotating freely. So in the vertical direction, the angular momentum is conserved. But initially, because the axis of the wheel is in the horizontal direction, I don't have any angular momentum in the vertical direction. But as soon as a person rotates the axis such that the wheel now has the axis pointing in the vertical direction, the wheel has the angular momentum in that direction, right? So initially, the total L is 0. And finally, there is an angular momentum in the Z direction due to the wheel. But since angular momentum has to be conserved, that means the angular momentum of the wheel together with the angular momentum of the person added together must be remaining 0. But since the wheel rotates in one direction, say in the clockwise direction, the person must have the angular momentum in the opposite direction. So that the angular momentum of the person must be pointing downwards. If the wheel has an angular momentum pointing upwards, the person must have an angular momentum pointing downwards. Okay, so that means if the wheel rotates in clockwise direction, the person is rotating in anti-clockwise direction, and vice versa. If you flip the whole thing, the wheel now have angular momentum pointing down, and that means the person angular momentum will be pointing up. They always rotate in the opposite direction to maintain the initial 0 angular moment, total angular momentum. Okay, so that is an interesting demonstration that I really want to show you, but I cannot do it now since we are not seeing each other face to face. That's a pity. Okay. This is extension part to the discussion of angular momentum and torque and analog of Newton's second law. Okay, and you can also go to the extension part of the Euler-Lagrange equation. That is an interesting way to derive the Newton's second law for rotation. Okay, this is extension for you to learn more. And in the end of this chapter, we have left with a vector formulation. Now, this is a more rigorous formulation of the concept of angular momentum. I declare to you that I will not test you in your exam. Okay, I will not test you about this in the exam. I just want you to have a rigorous, more mathematical understanding of the mathematical structure behind all my discussion. Okay, so you have a better understanding of it. Okay. Now, first, I claim that finite rotation is not a vector. You may ask me why. I will illustrate to you why finite rotation cannot be a vector in a very simple way. I use a book. Suppose now I have a book lying on the table. The face of the book is facing upwards. I call this axis y-axis. And then I call the other two axes, which is on the plane of the book, as x and z axis. Okay, so that is the initial configuration. Now suppose I rotate the book 90 degrees about the x-axis, which is this axis. So the book will have its face now facing you, right? I now rotate the book 90 degrees about this axis, so the book is now facing you. And then I rotate the book 90 degrees about the vertical axis, which is the y-axis. So the book will become something like this. It will be have its edge facing you. So that's the result when I rotate the book 90 degrees about x-axis and then 90 degrees about the y-axis. How about if I do the opposite? If I reverse the rotation, the order of the rotation. Now, if I first rotate the book about the y-axis, the vertical axis, the book will become like this, right? And then if I rotate the book about the x-axis, it will become facing me like this. Okay, it still is facing me, but with the direction rotate by 90 degrees, right? Now, obviously, you can see, compare these two configurations. They are not the same. So that rotation is the finite rotation is not commutative, which means that if you rotate the x-axis about x-axis first and then rotate about y-axis, the result is not the same as rotating about the y-axis first and then rotating about the x-axis. The two operations simply do not commute. They do not produce the same result. But vector addition itself is commutative. If you treat the angle, the rotation angle as a vector, you must have theta x plus theta y equal to theta y plus theta x. The addition of two vectors is independent of the order of the two vectors. But this rotation result actually violates the commutative rule so that it cannot be a vector. So finite rotation can't be a vector because it's violate the commutative rule. Okay. Now, what is how to save us? If rotation is not vector, then it would be problematic. Now, fortunately, although finite rotation is not a vector, but infinitesimal rotation is a vector. If you take the angle to be extremely small, if you count only to the first order of the rotation, you write out a rotational matrix in mathematical form, and you will find that the rotational matrix about any two directions will be commutative. Okay, of course, to the first order in the angle delta theta. Okay, and so infinitesimal rotation is a vector. Right? I skipped the proof because it is too involved with the mathematics. I don't want to introduce to you the rotational matrix at this level. Okay, so I skipped the general proof. I only want to let you know that the theta is a vector. It can be written as a vector. But angular velocity omega is d theta dt, right? So that means angular velocity is a vector. Okay, because angular velocity depends only on infinitesimal rotation, but not a finite rotation. So it can be a vector. Okay. Now, as we say, we define angular velocity direction in this way. When the body is rotating about an axis in this direction, I use my right hand. If the body rotates along this direction, the direction of my thumb will be the direction of omega. Okay. Now let's define it. Let's define the relationship between omega v and the position of the object by the cross product. Okay, because I use the right hand rule that somehow involves a cross product, and the relation is like this. If I now define origin here, the origin can be arbitrary. It's not necessary for the origin to lie in the same plane as a plane of the rotation. The origin can be lower than the point of the center of the rotation. Okay, and at this instant, I have a vector pointing out from the origin to the point mass here, which I call r. And the angle between vector r and the angular velocity omega, I call it the angle theta. And you can see from this diagram, the velocity vector is tangential to the circle. So the velocity vector is here, tangential to the rotating circle. Okay. I claim that V, R, and omega, they're related by this cross product. V is equal to omega cross R. Now, why is it so? First, I look at the direction. If I start from the vector R, which is in this direction, I cross with, if I start with the omega vector, which is in the upward direction, I cross with the vector r, I will find that the cross product will give me a direction in the tangential direction, which is the direction of v. So that the cross product is right, this formula is correct in terms of the direction. The direction of omega cross with direction of r actually gives me the direction of the v, which is tangential to the circle. And the second thing is to look at the magnitude. If I look at the magnitude, then v must be equal to omega r multiplied by the sine, the angle between the omega and r, right? So it's omega r sine theta. But what is r sine theta? You look at this triangle. This is a right angle triangle. This is the radius of the circle. And this angle is a right angle, okay? So r sine theta is the radius of the circle. So r sine theta is r pro. So it is omega r pro. Omega multiplied the radius of the circle is a linear speed. That is the basic formula for circular motion. So that must be correct. Okay, so both in terms of direction and in terms of magnitude, this formula is correct. So OV is equal to omega cross R. Okay. And we can define the torque by using a cross product. Now, in our previous discussion, we have this diagram, right? The force is in this direction, so we resolve a component of the force in the perpendicular direction, and R multiplied by F per give me the torque. Now, I also want to include the direction. I use the right-hand rule again. I have my vector R pointing outwards, and when R cross with F, it is pointing out of page. But that is exactly the direction of rotation. The torque actually tends to rotate my body along the direction of my forefinger so that the torque is pointing out. So the direction is correct now. If I use my right-hand rule, the torque pointing out actually means the force is rotating the body in the anti-clockwise direction. Okay, so I now have R cross F as a torque. And I also have to check the magnitude. The magnitude has to be consistent of what we defined previously, right? So I have F per multiplied by R, but F per is F sine phi, if phi is this angle, okay? So eventually I have F R sine phi, but F R sine phi or F per R is what? It's just the magnitude of the cross product. R cross F actually has the magnitude of F R sine phi, because phi is the angle between R and F. So it's R cross F has a magnitude F R sine phi, which is correct. Okay, so the torque can be defined this way. Now, similarly, if I have angular momentum, I can define the angular momentum by a cross product between the R and the linear momentum. I have R cross P, and it's defined exactly by the same diagram. Okay, R cross P gives you the angular momentum. Now, in short, whenever I meet quantity, the angular quantity, I define it with a cross product. I define R cross F as a torque and R cross P as the angular momentum. Okay, I just form R with cross product with the linear counterparts, and I would like to have the angular quantity. R cross with the force give me torque. Cross with the linear quantity give me the angular quantity. Okay, again, the R cross with the linear momentum give me the angular momentum. Okay, now if you accept this definition, okay, if you accept V equal to omega cross R, torque equal to R cross F, and L equal to R cross P, you will find life much easier. Why? Because we'll be able to prove Newton's second law for rotation of a non-rigid body very easily by using this definition of torque and angular momentum. Let's see why. Now, if we start with the angular momentum in this form, R cross P, okay, then we differentiate. Now we have a single particle with angular momentum L equal to R cross P. Now we differentiate. Now, how do we define a cross product? Now, the answer is when we differentiate a cross product, the rule of the differentiation is just a product rule. Because when we take the component, we find that each component will just is a product of two quantities, one quantity from R and one quantity from P. So when we differentiate it, we are just differentiate a product of two scalar quantity. And so the product will apply. And after you apply the product rule to each of the component, you group them up, and you will find that eventually the cross product itself will obey the product rule, just like the scalar quantity. Okay, so you can apply the product rule to the cross product R cross P when you differentiate it. If you apply the product rule, then you first differentiate the R with respect to T, cross with the P, plus you keep the R intact and cross with the derivative of the linear momentum P. So you have the R cross P plus R cross dP. Okay. Now let's examine what is the R dt cross P. The R dt is the velocity. So you have the velocity cross with the momentum. But the momentum itself is the mass multiplied by the velocity. So you now have the velocity vector cross with the velocity vector. But if the two vectors are parallel to each other, the cross product is 0, right? Because the angle between them is 0, so the sine the angle is 0. So V cos V is 0. So the first term vanishes. For the second term, you have dP dt now. But dP dt is the force F by Newton's second law, right? So you have R cos F on the right-hand side. But as my definitions say, R cross F is a torque, right? That's how we define a torque. So that means what? That means R cross F can be written as torque. And torque is now equal to the rate of change of angular momentum for a single particle. So you now prove the Newton's second law in a rotational form for a single particle. The torque acting on that particle will become equal to its rate of change of angular momentum. Now let's be more ambitious. We want to prove it now for a system of particles. Imagine now we have n particles. They are not a rigid body. They can the whole thing can be deformed, or even all the masses can be moving randomly. They can be moving arbitrarily in any direction. So that's a very general setting. Okay, we do not only relax the condition of a non-rigid body, of a rigid body. The body can be non-rigid, and it can be consist of even gas molecule that can be moving randomly in all directions. Okay, so that is the most general setting for Newton's second law for rotation. And the total angular momentum of this system, for each particle, the angular momentum is Ri cos Pi. That is the angular momentum for the I particle. Now, if I form a summation over all the particles from 1 to n, I will have a total angular momentum of the system. Okay, so L is simply a summation of over I, Ri cross Pi. Now I differentiate both sides of the equation. When I differentiate L, it gives you the rate of change of the total angular momentum. When I differentiate the right-hand side, I can distribute my operator to each of the particle so that I apply the product rule as usual. And the first term will give me the Ri dt cross P. The second term will be Ri cos dP dt. Okay. Now we have the summation, but that doesn't matter. The summation can be distributed to each of this term, right? So we have the same thing as before. Now I find that the first term is 0 because the Ri dt is V, right? It's Vi. Vi cross with Pi is just Vi cross with Vi, right? Apart from that M. And so it is 0 as before. And so we have what? We have only a second term. For the second term, the Pi dt is the what? is the net force acting on particle I. So I write it as Fi. Okay. And so I have the rate of change of the total angular momentum as summation Ri cos Fi, right? And that is summation of the torque. By definition, Ri cos Fi is a torque acting on particle I. Now, but we must be careful about the torque, because the torque can be divided into two parts. I can write the torque acting on particle I as a sum of two torque. The first torque I write a subscript E to denote that, superscript E to denote that it is external torque acting on particle I due to an external agent. Okay, so this is the torque coming from the outside the system. Okay, and I call it the external torque. And there are also internal torque. What are the internal torque? The particle within the system may interact with each other. They may be colliding with each other, or they may have long-range attractive force or repulsive force. So they may be interacting with each other. And when they interact, they exchange angular momentum. They exert torque on each other. So these are the so-called internal torque. And I use a symbol tau ij to denote the torque acting on particle I due to particle j. Particle j is another particle. Now I'm considering the torque on particle I. That includes the external torque and the internal torque due to all other particles. And because there are many, many such particles, I form a summation of this internal torque over J. J is the index denoting all other particles acting a torque on particle I. Okay, so torque Ij is the torque acting on I particle due to the J particle, and summation is the total internal torque. Okay. So I have now this equation with torque divided into two parts: the internal torque and the external, external torque. Now, if I put back the torque into this equation, I have a double summation for the second term, right? When I form a sum of the torque of all the particles, for the first term, I got a total external torque because I'm summing up all the external torque on the individual particle. So the torque is the total external torque, is from the outside. But I also have the internal torque. And I form a double summation now. I sum over the two index. I sum over the torque, the I index and the J index. And I find that this sum eventually will go to 0. Now, why is it so? The problem is when I form a sum, a double sum of all the index, that means I and J may both run over 1 to n. Okay? And suppose if there is a term when I is equal to, say, 5, when I is equal to 5, and J is equal to 6, then I have the torque of 5, 6, right? Here, the I is equal to 5, and J is equal to 6. I have this term, right? But since I and J are both running through 1 and 2n, that means I will have another term with I equal to 6 and J equal to 5. I must have this term, right? With the two index invert. And I claim that tau 5, 6 and tau 6, 5, they add up together to 0. And so in this summation, all the opposite pair, tau ij and tau ji, they always be canceling each other. And so the total torque, the total sum of tau ij will be 0. And now I'm going to prove that. Now I consider interaction of particle I and particle J. They interact together with each other with an internal force, Fij and Fji. Okay, Fij is the force acting on particle I due to particle J, while Fji is the force acting on particle J due to particle I. And since they are internal force, they obey Newton's third law. Okay, in this diagram, I draw an arrow in the opposite direction, meaning that they are equal and opposite. Okay. Now I consider torque Ij. I consider torque Ij first. Torque Ij is the position vector of the I particle Ri crossed with Fij. And how about the torque acting on particle J due to I? The torque Ji is the position vector of the J particle Rj crossed with Fji. So the sum of these two terms, tau ij and tau ji, will be equal to Fi F crossed with Fij plus Fj crossed with Fji. But since Fij and Fji are equal and opposite, I can reverse the index. Instead of writing Fji, I now turn it into Fij, but with a negative sign. Because they are equal and opposite, I can always replace Fji by minus Fij. Right? Now I can extract a common factor. In this two terms, I find that there's a common factor Fij. And in the bracket, I'm left with Ri minus Rj. But what is Ri minus Rj? Ri minus Rj, according to this vector diagram, is the vector that points from particle J to particle I, is this vector. Now you can notice that if the two particles interact with each other with a force in the direction, along the direction, joining the center, then Ri minus Rj must be either parallel or anti-parallel to Fij. And it means that the cross product is 0. Okay, when the two vectors are parallel or anti-parallel, the cross product is always 0. And that means the sum of the two internal torque will always cancel each other. So that's why tau 5.6 and tau 6.5, they cancel. And similarly, tau 6.7 and tau 7.6, tau 101 and tau 100, they cancel in pair. Okay, and so that this double sum always sum up to 0. And what is left over is a sum of all external torque acting on the particle, and that is a total external torque. The internal torque doesn't matter. It will not change the total angular momentum. So the proof here only says the internal torque will all cancel by Newton's third law. Okay, and eventually I have the Newton's second law for rotation in the most general form. It applies not only to a rigid body, it applies to a non-rigid body, and it even applies to a system of particles moving arbitrarily. It even applies to a gas particle. As long as this gas particle interact with Newton's third law, this law will apply. This law of Newton's second law for rotation will apply. And in this form, we have the torque be equal to the total rate of change of the total angular momentum. And tau L are both in vector form. So it applies to arbitrary distribution of mass moving arbitrarily. Even if they have no fixed axis of rotation, they may deform, they may be moving arbitrarily. They do not need the fixed axis of rotation. There may be gas moving arbitrarily. And this form of Newton's second law still hold. Now we restrict this law to a special case. Suppose the body is now rotating about an axis. Okay, like a skater, the skater is rotating about a fixed axis. And in that case, I can write the angular momentum is I multiplied by omega. Okay, where I is the moment of inertia about an axis of the body. And with this special case, I can rewrite this formula as tau equal to dt I omega. Now the dt act also on the I. The I may change with time, but we have already proved it. Because I omega is only a special case of L, and I've already proved the most general situation of torque equal to dL dt. I can now apply to a special case of a changing I. Okay, so this formula, now I prove it. Okay, it holds even if I change with time for a non-rigid body, for example, a skater. Or even there are situations where the angular momentum direction will change direction. That is, for example, a spinning top. Now, I'm not going to talk about the spin torque because it will spend too much time. But for that situation, I also will have this law hold, okay? And when the total external torque is 0, we have the law of conservation of angular momentum, which means that the vector sum of all the angular momentum of the system will be equal to a constant, okay? So we should understand the phenomena about torque and angular momentum. We always think about them as vectors. And I will not talk about gyroscopic precession at the end of this chapter because it takes too long. We don't have enough time. But even though you have the appreciation that the vector nature of all those rotational quantity. So that is the spirit of introducing this general setting to you. Okay, now let's stop here. I think it's time's up.